Welcome to a very special Chemistry 112. Sorry, not meeting at the usual time, but this video will serve as in place of the standard lecture. So what am I going to do in this video? Well, I'm probably not going to take the whole hour and a half. What I'm going to do, I'm going to start by going over 3 problems and on the Chapter 13 homework, a quick reminder about the test, then starting a bit into Chapter 14, at least the easy stuff. Chapter 14 is all about kinetics and reaction rate. And so we will get there shortly. The first thing we need to do is go to achieve. The 3 problems I'm going to go through are problems 12, problem 13, problem 14. Problem 12 is standard freezing point depression, but there's a little bit backwards. And so that's one of the reasons why we'll attack this one, because it's very similar to what we have on the test. So try this one again. This one working a little bit in reverse, where we have a desired freezing point with sucralose C12, H19, Cl3, O8. I've already pre-measured this, and the molar mass of this guy happens to be 397.35 grams per mole. And we want to know how much sucralose do we need to melt 3 kilograms of ice at negative 11 degrees. I've already know the KF. So we're working with this. Delta T equals negative I KFM. So the first step here is if we know the delta T is negative 11, and it tells us to assume I is 1, and we know KF is 1.86, what is M? M, so we're going to take 1.86, negative 11 divided by 1.86, and so by doing that, you get M is 5.91. Now, M is in moles of sucralose and kilograms of water, which is so moles over 3 kilograms, solving for moles. So 5.91 times 3 gives us 17.74 moles. The final step here, 17.74 moles. Set that up with our molar mass, 397.35 grams over 1 mole. Setting that up, we get that you should get, it's like 7,049 grams. A very, very large mass, but you got to remember, you're making water freeze at negative 11. So it's a very big change. Looking at that. Number 13. Using similar thing, we're using sucrose, C12H22O11. What is the osmotic pressure given this molarity? 0.151 molar. And 37 degrees. Well, this one's actually a little bit easier. Actually, a lot easier. IMRT. Note they want this in atmospheres. So because they already give us the molarity, we don't need the molar mass of sucralose. So we can just figure out, because it's sugar, big, large, organic, I is 1. Molarity is just 0.151. Because they ask for atmosphere, we use the 0.08206. And the temperature needs to be in Kelvin. So the only thing that we really have to do is turn 37 degrees to Kelvin. So that's 310 Kelvin. So 310 times R times 0.151. The pressure is actually not that bad. 3.84. Not too difficult there. 3.84. The last one is, once again, a tricky one. We're going to work our way backwards to find the molar mass. This is something similar to what we're going to do in lab. So in lab, they say 2.50 grams of a non-electrolyte solution is dissolved in water to make a 235 ml solution at 24 degrees. Okay, this is with osmotic pressure, 24 degrees. So osmotic pressure is 837 torr. So what is the molar concentration? So non-electrolyte. So they tell us I is 1. They tell us osmotic pressure. They tell us temperature. But one thing we'll have to do is turn torr into atmospheres. So 760 torr is equal to 1 atmosphere. So that's the first thing we're going to do. But they're going to ask for first concentration, then moles, then molar mass, just like the one we just did. The first thing I'm doing is I'm converting 837 to atmospheres. 1.1013 ATM. 24 degrees is 297 Kelvin. Okay. With osmotic pressure in mind, we have 1.01013 equals 1 times M times R, 8206, times T, 297. With that in mind, what is our molarity? So take our 1.1013 divided by our R divided by our T. We'd get the molarity for this solution would have to be 0.045, let's say 19. Now the next thing they ask is, what is the moles? To do molarity to moles, you're going to have to multiply that by the volume. So the volume is 0.235 liters. I turned 235 milliliters into liters, and that would give us what mass that would have to be. Our moles would be 0.01062 moles. And finally, to get molar mass is equal to mass over moles. So if we have 2.50 grams and we had 0.01062 moles, that will give us a molar mass of 235.4. So let's try that in the context of this. Our molarity, we said, was 0.04519. Moles then become 0.1062, and our molar mass was 235.4. Checking the answer. That is how we would go about doing that. We are not going to do the next one, but this one is you're just looking at freezing point. If equal concentrations, complete dissociation, you're looking at how many ions does each break apart into. So we're not going to worry about that. Instead, we're going to start chapter 14. Before we start chapter 14, though, we are going to discuss the test for a minute. Our test is, once again, due this coming Tuesday. You have time to work on it. You're free to work with other people. But the one thing I want you to do, show your work. Learn how to do it. If you need to ask a question about pointing in the right direction, I can do that. I found this will sometimes help you more understand this if you are forced to sit down and reason through this. Try to work through it. It is possible. You should do it. Showing work gives you partial credit. The important thing is that make sure you're reading the question, answering the question that I'm asking you. Waiting for the chemical kinetics here. What we're looking at is the speed of which a reaction goes. Trying to understand it. The whole idea of this chapter, up until now, we've kind of only been concerned with what reacts. We want to know how many atoms of this reacts with how many atoms of that to form how many atoms of that. We didn't really care what was going on. And we cared what was going on, but not really so much how it actually occurred. So that's one of those big things that will change in this chapter. Not only do we care what's happening, but we're going to care how fast it's occurring, because coal going to diamond or diamond going to coal, knowing whether this is going to take minutes, hours, days, years, centuries, kind of important. On a really important thing, you could be turning like plant into like dead dinosaurs into fuel, but you have to, if it doesn't happen quickly, that doesn't do us any good. So we're going to be looking at rates of reaction. It's going to get into a little bit of calculus. I'm going to try to skim over it as little as I can, so that you don't have to actually know a whole lot about differential or integral calculus to do this, but just know that we will be dealing with this. So the first thing we need to remember is we're going to measure a reaction rate, which is defined at the speed of which a reaction occurs. It's going to be the main topic in this chapter, but we will get into mechanism as well, because mechanism will affect the reaction rate. So the first thing that's going to affect the reaction rate is the physical state. Basically, if you remember, atoms have to collide in order to react. So the larger surface area you have, the greater the mixing, the faster the reaction. Two solids are not going to really react with each other unless you stir them together. Two liquids, if they're miscible, they will mix, but not too much. In the case of our lab that we just did with oil and sodium hydroxide, they are not really miscible. We had to use a solvent that would dissolve both, and even then we're required to stir that while heating to make it go. Otherwise, it would only react on the surface where they contact each other. If you have gases, gases mix without any real need to mix, without any actions done by us. So those gas reactions will happen the fastest of all. And so the nature of the reactants will be important, whether they're stable or highly reactive. It's essentially how much potential energy is stored up, how easy is it to break those bonds. The strength of the bonds is going to control how fast they go. Concentrations is going to be the main thing we will look at, because concentration is something we can very easily control. Long story short, the more reactants you have, the faster it will go, because the more you can mix. If you need one atom of A to find one atom of B, and you only have one of each, and you have a big solution, it will take a while of bumping into the solvent molecules before they find each other and collide. But if you have a million of each, it'd be very easy for them to find each other. The temperature is something else we can control. Long story short, the more temperature we have, the more energy. The more energy, the faster the reaction, the more likely they're going to collide, and when they do collide, break bonds. Though in general, this is a hard and fast rule. It's not perfect, but it works. But every 10-degree temperature difference will double the reaction rate. So how fast it will go. And in fact, if you look at the data for the various vaccines for COVID-19, the stability of these vaccines follows this rule pretty well, that room temperature, the Pfizer is only stable for about 6 hours. When you get it down to like basic refrigerator temperatures, it's stable for several days, maybe like a week or so, and maybe a couple weeks. And then when you get it down to sub-zero temperatures, essentially stable almost indefinitely, because each time you're doubling the time it takes for it to decay. So every 10 degrees, you're dropping the temperature. It's doubling the time it takes to decay. So double 2 weeks, you get a month. Double a month, you get 2 months, then 4 months, and so on. And finally, the presence of a catalyst. The catalyst we'll talk about near the very end, but catalysts will just greatly speed up the reaction rate, period. But in general, anything that increases the amount of collisions will increase the reaction rate. So more surface area means more collisions. More atoms mean more collisions. More speed means more collisions. All these are going to contribute to the rate. Now, how do we actively measure the rate? The rate is going to be measured as the speed of a reaction. Now, if we're talking about distance traveled, like speed of a car, we talk about miles per hour, kilometers per hour, meters per second. All those are rates of speed with relation to vehicular momentum, or us. Now, with a reaction, we're going to look at as a molarity per second. We can look at it as atoms per second, but more commonly as a molarity per second. And so this is going to be the speed of a reactant consumption. So how fast is the reactant being used up and then going away, or the speed at which a product is formed. But regardless of what we're looking at, the units will not change. I mean, it will be a molarity over a second. Just note that if it's an increase in concentration, we'll be seeing a positive rate, and a decrease would be a negative rate. Just like if we're accelerating in the car, we'd see a positive acceleration. Decelerating in the car, we'd see a negative acceleration. So it's whether the reaction rate is accelerating or decelerating because we're looking at either reactants or products. Now, one of the things to note about stoichiometry in kinetics, looking at a general reaction of 2A goes to B. So 2A molecules go to B, like a hydrogen atom and a hydrogen atom fuse together to form a hydrogen element. Every time the reaction turns over, 2 atoms of A react and form 1 atom of B, or 2 moles of A goes to 1 mole of B. We can look at the concentration of both in relationship. We see A decreases as B increases on this graph, and that A is decreasing at double the rate that B is increasing, and it's getting half the height. B is getting half the height that A has achieved. Eventually, it will level off as A goes to 0. But we can look at these reaction rates in relationship to each other based on simple this simple based on this simple relationship that looking at a generalized rate for this reaction, the rate of A is twice as much as the rate of B. So if I take the rate of A, we'll say it drops like 5 per second. The rate of B would be 5/2 per second. So every time 5 A's go away, 2.5 B's form. So we can look at the relationship of -1/2 rate A, change in A over change in time equals the change in B over the change in time. That's what this relationship looks at. Take a similar equation. A goes to B and 2C. So A degrades down into 3 different products, 1A and 1B and 2C. Every time A is consumed, we produce 1 molecule of B and 2 molecules of C. See right there, if we look at the graph, A is being degraded, B is being formed at a similar rate, it's getting about the similar height. C is doubling up, going twice as fast as B and reaching twice the height as B. So we can relate that negative change in A over change in T time is equal to positive change in B over change in time, which is equal to positive 1/2 change in C change in time. Because C is twice as fast, we need that 1/2 to make them equivalent. So this is going to be true for every reaction, regardless of how complex it is. We can generalize a formula for any reaction, any situation, that for a element or compound A and an element or compound B, the rate is equal to -1 over small a, which is our stoichiometric coefficient for A, and equal to +1 over B, the stoichiometric coefficient for B. So negative for reactants, positive for products. Doesn't matter what the coefficient is, we're just going to divide by that coefficient. So from this, the quantity of all compounds could be determined through the measurement of any one of those compounds. What this generalized means is that if I know one thing about a reaction, I know everything about that reaction because the reaction rate is constant with regards to all molecules in there. That if I know how much A is left, that there's 50% A has been consumed, we know that 50% of all possible B has been consumed. We know that 50% of all possible C has been formed, and that would be double the concentration of B. This is going to be used typically when we look at light absorption and Beer's law. That Beer's law is absorbance equals the molar absorptivity times path length times concentration. if even one compound absorbs light, then we can determine all concentrations with respect to that one that we can measure, because they're all being consumed at the same rate, unless they are, for example, catalytic. So just looking at this, a generalized reaction rate for 5MnO2, 4H plus, 3Mn2 goes to 3Mn2 plus, 2MnO41 minus, and 2 water. If the rate of consumption of manganese dioxide is 20 molar per hour, what is the rate of proton consumption? So let's write this down. So 5MnO2, 4H plus, goes to 3Mn2 plus, 2 permanganate, and 2 water. And we say the rate. So the change in MnO2 over change in time is 20 molar per hour. And I ask, what is protein? It's protons. What is just straight up manganese? And what is manganese permanganate? Go into that. If that's that, so we can say that times 1/5 equals the rate of hydrogen over 1/4. That'd be negative 1/5. That'd be negative 1/4. We look at manganese, 1/3 delta for the manganese for delta T. And if I continue going there, so we lose 20 an hour. And be 1/2 delta permanganate delta T. So looking there, negative 20 divided by negative 1/5 is positive 4. To solve for this guy, we're going to have to multiply by negative 4 over 1. So 4 times negative 4 for hydrogen, it's going to be negative 16 molar in an hour. So 4 molar per hour times positive 1/3. So for manganese, positive 4 times 3 is 12 molar an hour. 4 times 2, so permanganate is just going to be 8 molar per hour. That if you looked at these, you could thus measure them without care. As long as you could measure one, you knew the others. Now, this is the simplest. This is the easiest thing we can do in this chapter. It's only going to get harder from here, so bear with me. Bear with me. So as we look at this, we are going to measure rates of reactions. You could measure the average rate, but that doesn't do a very good job, because depending on how long you measure it, you're not going to get a good slope. The idea is, like, if I measure it initially, it's really fast, and you see the slope of the line starts to decrease as the reaction goes. If I measured the rate right here, by the end, the reaction is almost nothing, because we have almost no reactants left. So oftentimes we are going to want the instantaneous rate, which is the tangent to the curve. This is where we get into the calculus. Tangent to the curve is a line that only touches the curve in one spot. And so it's the most accurate representation of a slope at that given instant. And so typically scientists will only prefer the instantaneous rate at the initial time. They'll only look at the initial rate where the reaction speed will be the fastest. So I'll be looking at, for example, this portion right here, if at all, if it not even less, the region where it's the fastest, to try to determine stuff about that. So one thing we will do is trying to determine a rate law, because here is where it gets a little tricksy. That we can use a rate law to describe the reaction rate based on reactant concentration. A generalized rate law should look like this. The reaction rate is equal to K, which is a constant, A to the superscript of M. A is just a compound. Superscript M is a reaction order, times B to the superscript of N, where it's a reaction order. So if we're saying A plus B goes to product, I'm including only as many compounds that are on the reactant side. Now, this is where it's hard. The order, reaction order M and N, and the reaction constant K have no relation to the stoichiometry, well, have very little relation to the stoichiometry of the overall chemical equation. If I look at a simple equation of nitrogen plus hydrogen goes to ammonia, the reaction would be 1 nitrogen plus 3 hydrogens go to forming 2 ammonias. We could talk all about the reaction rate, that the reaction rate of nitrogen would be, the rate of consumption of nitrogen would be exactly 1/3 the rate of consumption of hydrogen, because hydrogen has to be consumed 3 times as fast. The rate of production of ammonia would be twice as fast as the rate of consumption of nitrogen. But how the reaction rate depends based on the concentration of nitrogen and hydrogen has very little to do with the stoichiometry. So if you look at, these are actual experimental data. If I use 0.5 molar of nitrogen and 0.5 molar of hydrogen, the reaction rate would be 3.5. If I decrease the amount of nitrogen, the rate goes down to 1.4. However, if I decrease the amount of hydrogen, the reaction rate was still 3.5. And if I decrease the amount of nitrogen and hydrogen not quite as much, the reaction rate is 2.1. So the observed rate has certain dependence on how much nitrogen and hydrogen we initially start with. Where do we start on that graph as it starts to decay? Look at that. So these reaction orders are typically in integers, and the larger the reaction order is, the greater the effect of the concentration is. So if the reaction order is 1, there's a 1-to-1 effect on the reaction rate and the starting concentration. If it's 1 to 2, if the reaction order is 2, means the higher the concentration, the larger the effect on the rate, because it's the concentration squared. If we add all the individual reaction orders together, we could get what's called the overall reaction order. So the reaction order is kind of looking at how they affect the reaction. So we're actually going to determine some of these based on experimental data. Now, where this becomes problematic is that as I said, reaction order does not directly relate to the balanced chemical equation. This has to do with mechanism and actually a balanced overall chemical equation being made up of smaller chemical equations. Our reaction orders are going to fall into one of 3 categories typically: a zero order reaction, which is a reaction rate that is independent of the reaction concentration. So changing the reaction concentration does not largely change the speed of a reaction. First order, which it's directly dependent. And a second order, which the reaction rate is the squared factor of the reaction concentration. And these orders, with along with K, we can determine experimentally. How it's done in the lab is you take a reaction, you're measuring this, and you're going to vary the concentrations until you can get and vary the concentrations, and you'll see what happens to the reaction rate. So I'm going to continue through this, and we'll keep looking at this. So determine a reaction order. We're going to vary the rates of two reactants where only one variable is changed. This is something we will do in lab, like lab number 3. Something we will do in lab. So we'll compare the rate of one with the concentrations of one. What we can do. So you see, I've set it rate 1 over rate 2 is equal to K1 over K2, A1 over A2 raised to the power of N, B1 over B2 raised to the power of M. It doesn't really matter which one you call it, M and N. It really doesn't matter. Well, if we plug our numbers in and only A is changed and the rate has changed, you can, K is a constant. K's cancel out. If B is a constant between B1 and B2, it doesn't matter what M is, 0.5 over 0.5 is still 1. It doesn't matter if it's 0.5 squared, 0.5 cubed, 0.5 over 0.5 is still 1. So we can simplify this to rate 1 over rate 2 equals A1 over A2 and take the N outside of parentheses because both are raised to the power of N. So looking at that, if I set reaction 1 to reaction 2, see what happens. We saw the rate changed from 3.5 to 1.4 when the concentration went from 0.5 to 0.2. If you solve 0.5 over 0.2, that's a ratio of 2.5. 3.5 over 1.4 is also 2.5. So what we have is the rate change, which is 2.5, equals the concentration change, which is 2.5 raised to the power of N. Now, this one is easy. So 2.5 to N equals 2.5, only one. Sorry, N equals 1. And since this is a pure integer, it's usually an integer, it makes this a lot easier. Now, how do we solve this when the math gets ugly? And that's where we use a log-based rule. The log-based rule is that if a log is raised to an exponent, you can pull the exponent out front of the log and say n times the log. And so the first thing we do is we take a log to each side. We have to do it to each side to make them equivalent. So log 2.5 equals n times log 2.5. And then you divide by that to isolate the n. Why would you need to do that? Why would you need to do that? I'm going to switch back to the doc cam for a second just to set up. Just if we had something like this, instead you would have 2.5 equals, let's say 2.32 n. Because maybe we're using real world numbers, where it's not so perfect. Yes, they're pretty darn close. N is essentially going to be 1. But how do we do that? So we're going to say log of 2.5 was log n times log of 2.32. and we're going to divide log of 2.5 divided by log of 2.32 to find out what is our n. And of course, maybe round up or round down. And that's what we'll end up doing in the lab, because we're not going to have such nice numbers when we're dealing with lab-based data. Log 2.32, my n is essentially 1.088, which is approximately 1. So it's still there, but that's how we take care of it if it's not so easy that you can see it right away. But okay. Now let's look at this. Now repeating this with experiments 1 and 3. So we're always changing one variable, and then we do another experiment where we change the other variable, and we keep going. We keep going. Oh, in this case, we're looking at what happens when hydrogen change. Well, hydrogen changes when 0.5 to 0.2, the rate is 3.5 over 3.5, or 1. Now, a rule of exponents is any number raised to the power of 0 is 1. So how would you get it so that and the fact of log base 10 of 1 is 0? That how do you get 2.5 to equal 1? Only when m is 0. So what does this mean? So far, this reaction rate says that the speed at which nitrogen changes to ammonia is directly dependent on the amount of nitrogen present, and it's relatively independent of the amount of hydrogen present. So adding more hydrogen does not make this reaction go faster. The only way I can make this reaction go faster is by adding more nitrogen. More nitrogen. K is still unknown to us, but K is going to be easy enough to find. To find K, we plug in one experiment into this rate law and solve for K. In this particular example, I plug in experiment 4, which is the rate of 2.1 equals K times 0.3 times 0.4. 0.4 to the 0th. Because 0.4 to the 0th is 1, it becomes 2.1 divided by 0.3. So the reaction rate is 7 inverse seconds. The inverse second unit is there to cancel out all of our units and leave us with a rate being molarity per second, because molarity times inverse seconds gives us molarity per second. And here's the beauty of this. If done right, it does not matter which rate law you use. Going back to the DocCam. If I use experiment 1, 3.5 molarity per second equals K times 0.5 m times 0.5 m 0th, you get, let's just 3.5 meters per second, K, 0.5 times 0.5 m times 1. Isolating this, you get 3.5 molarity per second, 0.5 molarity. Molarity cancels. You get 3.5 divided by 0.5. That's going to be 7, 1 over seconds. Note, I did it with experiment 1. I did it with experiment 4. I got the exact same K. K is independent of which experiment I look at. We will do that each and every time. So we'll do this experiment, and that's probably where we'll call the class. It's a little early, but I mean, this is a video, and we'll start next class going over another experiment just like this to make sure you have followed along. I'm not sure how far you've gone in the video, but I want you to have semi-followed along. So we'll start next class with another video, with another experiment or example just like this. 0.3, I'm recording this in. So the process is the same each time. It doesn't matter how many reactants you have. If you have the process of everything, you have 3 reactants, you would have to look at 3 variables at a time. 3 variables at a time. Yeah, so changing only one at any given time. We have a generic rate law. Just rate equals K, we'll say A to the M, B to the N. Don't really care. So the first step is always to find the reaction order. The second step, once we find all the reaction orders, to find our K. So we need to look at which experiments does A change, which experiments does B change. Now A changes from in 1 and to 2 and 1 to 3, but it doesn't change from 2 to 4 or 1 to 3. But we also have to look at ones where if A changes, B does not change. So which one does B not change? B does not change in 2 to 3. Which ones does A change and B not change? We could look at, well, which one does B change and A not change? We could look at 2 to 4 or 1 to 3. Either one works. But let's look at our first set, experiment 2 and experiment 3. It doesn't matter which one I put over top. It doesn't matter as long as you keep the ratios the same. If that's 3 and that's 1, 2.45 divided by 1.47 equals K over K, 0.5 over 0.3 M, 0.7 over 0.7 N. K's cancel, B's cancel. So 0.5 over 0.3 is 1 2/3, or 1.67 to the M. 2.45 divided by 1.47. Well, that's conveniently 1.67. We're going to save ourselves a little bit of work and say just M is equal to 1. Now let's look at B. I'll go ahead and use 1 and 3. 1 and 3. 1. We have 2.45 divided by 1.25 equals K over K. 0.5 over 0.5 to the first, and 0.7 over 0.5 to the N. Those are going to cancel. Those are going to cancel. 2.45 over 1.25 is equal to 1.96. 0.7 over 0.5 is equal to 1.4. To the n. Now, because we know they're supposed to be integers, you could actually guess. You could actually try. Is n 0? No. Is n 1? No. So let's try. Is n 2? 1.4 squared is equal to 1.96. So n is equal to 2. However, we could do the log way. Log of 1.96 divided by log of 1.4 gives you 2. Either way, we have our order and our overall reaction order. Rate is equal to K, A to the first, B to the second. So this reaction is dependent on one A molecule and two B molecules colliding. Now we need to find our K. So I'm going to just go ahead and use the last one, reaction 4, just because I haven't used it. It doesn't really matter. 0.48 M over S equals K 0.3 M, the first, 0.4 M squared. So the first thing, 0.3 times 0.4 times 0.4 is equal to, K is equal to, K times 0.048 meters cubed, molarity cubed is equal to 0.48 molarity per second. Solving for K. K is going to be 0.48 M over S times 0.048 M cubed. Please note, this M and one of these M's cancels. And so you get K is equal to 10, 1 over M squared S. The purpose of the units are to get the rate in the correct units. Another way to present that is 10 M to the negative 2 S to the negative 1. But the purpose of that is to get get the reaction rate into the correct units. That is the only purpose. But that's what we will be doing. That's the first part of this chapter. I'll go ahead and stop there. We'll stop a little bit early. But so thank you for your time. Please watch through this whole video, the best of your abilities. And I will see you on Tuesday.